Okay, hello. So today we will learn about temporal difference learning. It's actually a very important concept in reinforcement learning all throughout. Um, and we will essentially cover the main concept of temporal difference learning today. And in the next class, we will finish the syllabus with some discussion on Q learning, which is essentially one kind of temporal difference learning. Okay, so so let's recall how we do policy evaluation. Now, recall both. We need to actually look at both the dynamic programming and Monte Carlo approaches. But in Monte Carlo, what we do uh, when we want to find the state value or estimate the state value given a policy pi, what we want to compute the expected value of gt, the expected return starting at state st is equal to s, uh, where we know that gt is the discounted return eventually, and in case of Monte Carlo, obviously we'll terminate because we only look at episodic tasks. But in the general definition is essentially this rt plus 1 plus gamma rt plus 2 plus and so on, which we can actually write as the next reward plus gamma times the expected return from the next state. So what we do in Monte Carlo policy evaluation is we want to estimate V of a state ST or S, um, and we sample GT repeatedly. Okay, so essentially this GT is what the V is essentially the expectation of GT, and we take many samples of such GT for this state, and then we average, right? So that's what we want to do for Monte Carlo. And what we do essentially is something like this. V of st, we update it as V of st plus uh, some step size, which is not constant. This n is the number of times we have seen this state s, right? Uh, Times the gt minus the current estimate. So what is, so this is essentially the current estimate plus some factor times the current sample minus current estimate. Okay, so then we update the new estimate. Now we discussed in the very in when we discussed Markov decision process, we discussed that this thing can be changed into a, let's say, a constant one. In fact, we discussed that in bandit problem. So this can be changed to something like a constant. So um, we can actually, let's say, take something called a step size equal to alpha and make it make the update rule as vst equal to vst plus alpha times the new value, or sorry, new samples return minus the expected return so far. This is nothing but we keep an estimate. This is our new example. So what is the difference? We multiply that by some small number, right? So essentially, we have an estimate. As we see new examples and so on, if the new example exactly is equal to our estimate, we don't change anything, right? However, if the new example is slightly more, then we increase our estimate slightly. If the new example is slightly less, then we decrease it slightly and so on. So this is what we do. Now this also can be Monte Carlo, but it's just a slight modification of the formula. And this is what we will do for temporal difference learning, but we'll combine this portion with this portion. So let's see how. Uh, what we do is, instead of updating with the new samples gt minus vst, we will do the following. We'll replace gt by rt plus 1 plus gamma gt plus 1. So rt plus 1 plus gamma, essentially what we want is we want the expectation. So gamma expected value of gt plus 1, And essentially we can write it as, um, yeah, we can write it as alpha times RT plus 1 plus gamma uh, VST plus 1. Okay. So let's look at what are we doing here. Why did we take GTs as samples for V? Because okay, just excuse me for one thing. In some cases this has become a capital. uh, in my slides I have been writing a small v, so I'll correct that later on. So anyway, so what we have been doing is we have been thinking that GTs are samples for V, S, T, and so the expected value of GT is same as what we finally want. So that's what we are doing. And here, what we instead do is, so we already know that GT is equal to RT plus 1 plus gamma GT plus 1. That means the expected return starting from the next state in this episode or in this run or whatever. Uh, and instead of GT, instead of keeping track of GT at all, what we will do is simply, instead of GT plus 1, we'll simply replace that by current estimate of VST plus 1. Okay, so this is the temporal difference learning update rule. So let's understand this very clearly. VST, the current estimate plus some alpha times the reward. So the reward plus the next, the expected return from the next step. This is my GT, right? So I simply take this estimate. So I just see the new reward, and I don't need to see what would have happened in the episode afterwards. I just see the new reward. So temporally, I just see what is the new reward, and currently what is my estimate afterwards. I subtract my current estimate of the current state. Okay, so this is and another key difference, of course we will see examples to make this more clear. Another key difference is we can update VST as soon as we reach the next state. So in Monte Carlo, what we need to do is, in Monte Carlo we need to complete the episode and then backtrack and update all the estimates. In this case, what we will do is we will update VST as soon as we reach ST plus 1. Somebody had a question? Okay, so let's see. Let's actually see an example, or before we let's actually do this thing. So essentially, what is happening is, this is the update formula. VST is equal to VST plus alpha times RT plus 1 gamma VST plus 1 minus VST. So essentially, you have states, right? So there are lots of states, and at some point of time, for some time step t, we already have some existing estimates for VST. So this is a state, we have some existing estimate for this state, this state, this state, and so on. So for all states, we have some existing estimate for their values. Now, in a particular episode, this is what happens. So with taking action AT minus 1, I get reward RT, and I come to state ST. Then I take action AT according to the policy I am behaving, right? So remember behavior policy and target policy. So we did not so far we did not distinguish between those two, but let's talk about behaving. So according to the policy I'm behaving on, I take AT, new action AT, I get reward RT plus 1, and I go to the state ST plus 1. Now I have all the values RT plus 1, ST plus 1, the current estimate of what is the expected return from this state, and obviously my previous estimate on this state. So now I can actually update all of them. So using all of them, I can update my estimate on VST. Okay, so I don't actually have to wait for this episode to end. In fact, I don't even need to think about episodes anymore. I just, as soon as I am at this state, but I'll still don't have the values for RT plus 1 and ST plus 1 now. So I have to still go on to the next state. As soon as I'm at the next state, I can update the values for the previous state. Okay. Similarly, then I take action AT plus 1 and I get reward RT plus 2. I go to state ST plus 2 and I can update the estimate for VST plus 1. Okay. And so on. So this is what will happen. This is called one step TD or TD0. So there could be generalizations of these, right? Obviously. So this is a one step thing. I can do more steps and stuff like that. But the one step TD is basically the basic
Sir,
TD thing. Yes.
sir, correct me if I am wrong here, but doesn't this network look like that of a recurrent neural net? I mean, on the folding and unfolding temporal difference learning. Can we do the same using a recurrent neural network?
What do you really mean there?
Because
Um,
here we are getting some unfolding step, right? Here our output from ST plus 2 is helping us to get update VST plus 1. So there is some relation between the past and the present. That's why we are saying temporal difference. So
Right. But in recurrent neural network, I mean, you can do both directions in recurrent neural network. But I mean, in that way, there is a similarity that one affects the other. But um, so there, the whole okay. I mean, that the whole uh, functions and all those things are pretty different, right? Although definitely these concepts, it's possible that these concepts can be applied into um, function approximation and so on. But as of now, I don't see the exact relationship between this and that. So it's not really the same concept. Okay, so it's possible that the concepts can be combined.
okay, sir.
Okay, I mean, but yeah, I mean, one can always find analogies. Um, uh, Instead, you start to. So let's actually do an example, and you will probably find analogies to many other things than RNN. So let's just see one example, which is a very standard thing in our life. Suppose we are running against time. Okay, so let's say I'm going to office and I have a meeting in 1 hour. Um, then the reward obviously is more if I can reach office early. And suppose, before attending the meeting, I have to do some preparation or I have some other work also. So basically, my time saving is what I want to do. So reward is amount of time left after arriving. So that may be 1 hour minus time taken for preparation or something like that. Or you can simply say minus time taken. Okay, so doesn't matter. But we will actually not compute the reward. Instead, what we will do is we will actually keep learning the estimated time to arrival. Okay. So we're not changing policy here. Suppose my policy of driving is still the same. Whatever the way I drive, I drive. I'm not really changing any policy. But it's just that at every step, I'm trying to estimate better. Okay, how much time will I take? And assume we have a step size alpha equal to 1 by 10 and discount rate gamma equal to 1. So that means basically there is no discounting, but alpha equal to 1 by 10. So let's actually see what happens. So there is a state S, time elapsed so far, and expected time of arrival based on previous learning. That means uh, I have experience on traveling through the same route again and again, so I kind of know what happens when there is a traffic jam or this kind, and so on. Right? So, I mean, let's say I'm not using really Google Maps. Obviously, Google Map can do much better things here. Probably using all these kind of algorithms, but let's say I know I have some my own learning about situations. So, what are the states? So, first thing is leaving home. Time elapsed so far is 0, and my usual estimate based on previous learning is okay. I'll reach office in 30 minutes. Okay, so this example is actually adapted from Sutton's book also as well, but I just changed the description slightly, um, and the calculation also slightly, just to make sure it's more relatable for us. Okay, so the next is I reach the car. So basically, when I start essentially, so let's say that's 5 minutes. So basically, I get out of home and I take the elevator and so on. So after 5 minutes, uh, 5 minutes have elapsed. So this plus five means from here to here how much time has gone by, and this is total how much time has gone by. Okay, so it's just a cumulative thing. Now I see that it starts to rain, and now I know that when it starts to rain, the traffic is going to be bad. So that's what my normal perception is. So then I think, oh, no, 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 I still need 35 more minutes. Now here is what starts to happen. Now this is some state. The ETA is 30 minutes. This is a new state. Next state, ETA is 35 minutes from here. So you see, I said VST and VST plus 1. Okay. And my reward, well, I have already lost 5 minutes. So my reward by now is -5. Right. Okay. So here, obviously, we are not talking about reward, but we'll just see. So what we need to do now is we need to learn. So far, I used to think that um, going to office takes me 30 minutes. That was my average calculation. But this is a new sample. And here what has happened, I have already spent 5 minutes, but even then, I now think it will take me 35 more minutes. So at this point, I think the whole thing is going to take 40 minutes. So since this is a new sample, so suppose I have learned my 30 minutes from some number of samples before, and this is a new sample. So I should adjust my estimate on this a little bit now based on the step size alpha, right? In case of Monte Carlo and a non-constant step size, what you would do if your previous 10 journeys took 30 minutes on an average, then total 300 minutes, plus this time you are now thinking 40 minutes. So 300 plus 40 divided by 11, right? So that's what you would do. But in this case, will not keep track of all those. We'll simply do an alpha thing. So what is the alpha thing now? So then what we have, this is our formula. VST is equal to VST plus alpha times the RT plus this gamma times, and gamma is 1 here. So basically the new minus next state's value minus current state's value. And in our case, essentially, the update formula can be formulated as update ETA of a state. So ETA we need to update of this state as the present ETA of the state, which is 30 plus 1 by 10 alpha times time to next state. That means how much time have I already spent plus present ETA of the next state. So the present ETA is 35 minus present ETA of the current state. So now what has happened is I have already spent 5 minutes and I think I'll take 35 more. So this is 40 minus current estimate was 30. So essentially what is happening, the error, it's also called TD or temporal difference error. We will not formally talk about TD error in this class, but this is basically the temporal difference error, right? So you can relate to that thing, right? It's an error, right? So what has happened is I used to think it is 30, but now I think it will take 40. This error, my alpha is 1 by 10, so I should add 1 by 10 times the error to my current estimate. So I'm going to make it 10 minutes by 10, so 1 minute extra. So now I learned that, okay, next time I leave home, I should not think 30 minutes. I should think 31 minutes. Okay, go on. So let's say then I go for some time, another 15 minutes. Okay. And somehow, although it was raining, the traffic was light, and I now have totally spent 20 minutes, but I only have 15 minutes journey left. So I've saved some time essentially. And so I thought 35 minutes now, but maybe I can change this right now. So it doesn't mean that. So now I see that, okay, every time it rains, I should not be so pessimistic. So what I should rather do is basically I've saved 5 minutes. If you do the calculation, you will see that then I can actually, mm, oh, did I do it right? Oh, maybe. So if I, so time to next state is, this is 40, but I should take 35. So it should be 5 minutes by 10. So 300, yeah, so 300 seconds. by 10, so 30 seconds, right? So basically I have I improve my estimate by 30 seconds. So yeah, this is right. And so on. So next, when I next after 10 more minutes, I again fall into a traffic jam, and so on. So basically, then in this 15 minutes again, let's do the calculation. Hopefully, I'm right. Uh, I update this estimate by 15 minutes 30 seconds, and then I enter the campus. I know that I have to reach office. It will only take 3 more minutes to reach office, and but then essentially the traffic jam. I thought I will take 10 more minutes, but even after 10 minutes, I see that 3 more minutes are left. So I need to increase this a little bit more again. So this is 3 minutes by 10 essentially. This is the 1/10 factor, and then so on. So essentially, this is what happens. So after this run, okay, or after this episode, my estimates now have changed this way. So next time I will start with these kind of estimates. So this is what temporal difference learning is doing in this case. Now, you can clearly see that here updating ETA is equivalent to updating the expected reward, because expected reward is just 1 minus this. So it is just a plus minus thing here. So you can, instead of R here, you can do a minus R that way. So it should not really matter. The key differences. So is this example clear to everyone? What is happening here?
So can you explain the traffic jam part again?
Okay, so it's the same thing that is happening. So let's say so we were here. Yeah, so you are here. So we updated the estimate for this. So, and then I exited highway, and I thought, okay, I have saved some time. Now, after 10 more minutes, what happens? That means total time spent is 30 minutes. I see a traffic jam in front of me.
So no, here was my doubt. I mean, after 10 more minutes, how can the ETA be 10? It should be 5, right? If 10 minutes have passed and previously ETA was 15, then after 10 more minutes, it
Right.
also
So
will
the
be traffic jam.
ETA is based on the state, and the state is traffic jam.
Okay, so
So
it,
when I was here, see, when I left home, I did not know it will rain. That's the environment which is not in my control, right? So when I left home, I did not know it will rain. So I went into a state which is raining. So I had to now, okay, so see what happens is when we start our expect when we start with some VST, we have a, in general, with a depending on a probability distribution that we are used to, there is an estimate of the time taken, time that will take, right? But sometimes what happens, things change, and that's part of the distribution, but that is what happened. So similarly here, I exited the highway and I thought that, well, I will reach in another 15 minutes. So after another 10 minutes, I should have only 5 minutes left. But then I suddenly see a traffic jam in front of me. Oh, then I say, oh no, there is a jam. So it will not take 5 minutes. It will actually take more for me. So probably 10 minutes.
so this is after experiencing a traffic jam, right?
After experiencing
Okay.
the traffic jam, right? So this is after I go into this state. So
Okay.
these are all states, and which are like, and then, but however, it's not that I was expecting a traffic jam right now in general, but it is true that I have had this experience before. Okay, so I've had this experience of traffic jam before. Now jams can be, very it can be a bad jam, in not so bad jam, and so on, and all those things. Or it can also be that all of these are new for me, so I start with an average estimate initialization and things like that. All everything is possible, but here it's more like we are considering a scenario where the agent, or I know what happens on the road. So then that's why when I see a traffic jam, I know that my estimate for this state is different. So then I update this here. So which means essentially, how is it backtracking? One step. What it means is that so far I used to think after I exit highway, I should take 15 minutes. But now there is one more sample of a traffic jam. So the probability of having a traffic jam is increased. So now from next time onwards, I should think, well, it's 15 minutes, 30 seconds, because sometimes there can be a traffic jam. Okay, so that is the point. And then,
Sir,
yes,
so these green values, initially they will be arbitrarily estimates of BS, right?
in at the very
And then
beginning, yes, yes.
we will converge to the more
Right.
realistic.
At the very beginning, yes. But what the example I'm showing here, it's like already some the
In
agent
between
has,
state.
yeah, in between states. The agent has some
Okay.
experience, but how do
Yes,
we
yes.
continually change our experience? I mean estimates based on our experience. Okay.
So by that update rule.
Yeah, right. So basically that's what happened here. After the traffic jam, I thought 10 minutes, but looks like I took actually 13 minutes. So even after spending 10 minutes, I just reached the campus, gate of the campus, which means I actually need 3 more minutes. And here nothing unexpected happened. So I just reached in time. Okay, so this is what happened here. Okay, so uh, let's discuss the advantages of TD learning compared to dynamic programming or Monte Carlo. First of all, similar to dynamic programming, TD learning has this recursive update formula, right? So dynamic programming, what does it do? From this state, because it knows the dynamics of the environment completely, it can actually look ahead in all possible next states and update the estimates that way. So basically, there is a recursive update estimates based on other estimates, right? We don't have to actually get exact rewards. We can update based on other estimates. So that's the advantage. But obviously, the other great advantage, I mean, that's the good part about dynamic programming. But how is it better than dynamic programming? Well, it doesn't need a model. It doesn't need the model. It can learn directly from the experience, which is very, very important actually. So that part is similar to Monte Carlo. So we are actually combining the two good things of these two approaches. Now, key differences with Monte Carlo is that Monte Carlo can update estimates only after one full episode finishes. And temporal difference updates online and incrementally compared to Monte Carlo, right? So essentially, every step, as soon as you reach a step, you update the estimate for the previous step. And that means this can be applied to tasks with very long episodes or which are not even episodic. So sometimes what can happen is Monte Carlo, some episodes can be so long that updating takes a lot of time, and TD will not have that problem. And the TD0 methods also converge to the correct prediction asymptotically. And practice, in fact, it converges much faster than Monte Carlo methods. Okay, so we will actually do this computationally on this particular problem. So let's discuss what this problem is. So this is a Markov reward process. It is similar to the Markov decision process, but in this case we don't need a policy, or we don't have the choice of action. So what happens here is, this is useful. These kind of things are useful for prediction only. So from this state, uh, basically what would be the value kind of thing, given a random policy. So you can assume here that all actions are random among the permissible ones. So what is the process actually? The process are, we have 7 states, 0 to 6. Um, 0 and 6 are terminal states. So it's an episodic thing. 0 and 6 are terminal states. We always start at 3. So this is my start. Okay, we start at the center, and then randomly I go left or right. Okay, randomly means with equal probability. I either go left or I go right. So actions are random with equal probability towards left or right. So essentially, this policy is fixed random. So that's why that's not really important. Now the reward is 1 for the right terminal state, that is 6, 1 for this state, and 0 for all other states. Okay. So essentially, you can think of this as, I mean, in some places it's given that a mouse is randomly going this way or that way, and there is some food here, but there is nothing else anywhere else. But if it goes there, then it kind of goes out of the room or something like that. So then, yeah. So given you are in some state, what would be the probability that you get the reward, right? So basically, that's it. Okay. So uh, So that's the case. So for example, an example episode could be like I start at 3, 4, 3, uh, again 4, again 3, then 2, 1, 2, 1, and then 0, and that's the end of the episode, right? So something like this could happen. Okay, so let's actually see the, just a moment, yeah. So this piece of code, it's not really well commented. Maybe before I give it to you, I will actually write the comments. Um, but you should be able to understand. I will just quickly describe the code, and our main goal right now is actually to see the results. Uh, so essentially what we are doing here, I have 6 states, sorry, 7 states, 0 to 6. The rewards are all 0 except the last one has 1, right? Next is simulation of the action. So if I is equal to 0 or 6, then an episode has ended, then I start the next episode. So basically I next is 3, right? Otherwise, the next is I draw a random uniform number from -1 to 1. Uh, Here I assume that I'm never going to get 0. The exact 0 I'm never going to get. So basically np dot sign will be a random number, either a random integer, either -1 or +1, right? So essentially given a state, I either go -1 or I go +1. I plus the sign. Here, the probability of getting exact 0 is 0. So let's live with that. So basically, if we are at the terminal state, then I start in the begin state, which is 3. Otherwise, I go either left or right randomly. Okay, this code is actually not necessary. Generate episode. This was I was just testing, so not necessary. So let's actually look at this portion here. Okay, maybe, or maybe I'll just show you some example of an episode first. So yeah, so this I need to run. Okay, so suppose 3, 4, 5, 6 could be one episode, or 3, 2, 1, 0 could be another episode, or well, though they're just the shortest ones, look like optimal policy, but this also could be 3, 4, 3, 2, 1, 2, 1. So these are basically episodes. All right, so now let's see what we do. I will actually implement Monte Carlo and temporal difference both. So I have two sets of values. One is value for Monte Carlo, np.1s times. So we start with the state values to be 0.5, half. Let's say the we initialize state values to be half for all states except the terminal states will have value 0. Similarly, VTD is value for temporal difference. Again, we do the same thing. The terminal states have value 0. N samples is nothing but for every state, how many samples have I seen? That is for the Monte Carlo update. Now I set alpha equal to 0.1 and gamma equal to 1. So these are parameters. Let's actually do a small 50. Let's say n equal to 50. How many states do I visit? So I start with state equal to 3. Episode, the current episode is just the list 3 so far. Now I keep taking actions for n actions. S1 is next of S, so the next state. So because I need to, because for the temporal difference, essentially what I need to do is I need to keep track of this state and next state, right? So S1 is my next state. In the episode, I append S1. Now there are two kinds of things going on here. For MC, Monte Carlo, if the state is terminal, then I have finished one episode, right? Then I have finished one episode and then I should backtrack and update the values for all states encountered in this episode. So let's actually, we can run only one of them. So let's look at this update MC code. So update MC is, I pass the value list of values, episode, which is a list of states, gamma and n samples. So this is not the constant step size. This is the standard n samples. So G is equal to 0. This is exactly the thing that we have done. T from length of episode -2 because we wanted to t -1. So that's why I do starting from length episode -2 minus, and then I go on until -1. That means basically it will be, if my episode, I mean, if I have 5 states in the episode, it should be like a 4, 3, 2, 1, and 0. And then my gaps are -1. So basically this is a range function. So G is equal to gamma plus G times the reward of t plus 1, RT plus 1. I also update the number of times I am encountering this particular sample, and I'm updating it. So this is the update MC. Let's also discuss the update NC const. Update NC const is nothing but, instead of the n samples, I pass the alpha step size. So it is actually simpler. So again, the same G, but V episode T will be V episode T plus alpha times G minus V episode T. Okay, so this is your 2 versions of Monte Carlo. Okay, so this is where I can only run one of them because I've only initialized one area. If I did both, then I could, I mean, I could actually have another, because otherwise if I run both, then they will get interchanged actually. So that will be a problem. Anyway, so the update TD is simply, I don't need the full episode anymore. So update TD is, I just need my present estimates V, the array V, which will be passed. This will be passed as that. Then the current state, the next state, the alpha and gamma. So all I do is Vs equal to Vs plus alpha times rewards S1, so next reward, plus gamma times the estimate for next state minus estimate for current state. Okay, so let's actually run this. So what am I doing? If the state is non-terminal, sorry, if the state is terminal, then I am updating Monte Carlo for this whole episode, and I'm setting episode to null. I mean, basically empty list. However, for temporal difference, I update for S if the state is not terminal. Okay, if the state is not terminal, S1 can be terminal, but this particular state that I'm updating for should not be terminal. Then I update it. Okay. So yeah, anybody had a question? Somebody was trying to say something. All right, so let's run. So I'm only printing VMC 1 to 6 because I'll never really update the 0 and 6. So I only need to see 1 to 5, the states for which I'm interested. So if I run it for 50 actions, doesn't mean 50 episodes. Okay, so we can actually print what episodes we went through. So let's do that. Maybe let's switch that on. Okay, so maybe I print what episodes I went through. So I actually went through 3 episodes, and in that, what MC did was, MC did this kind of change. So it's not really much to look at. In fact, it's more interesting to actually show you this portion this way. So whenever I update MC, let's actually print V. Okay, and let's actually do that for a very small, and let me say MC, MC V, and here let me say print TD V. Okay, so that way, and then let's run it for, let's say, 10 actions. And okay, so see what has happened is, so far MC has not something went wrong here.
So you have printed in that MC constant, I think. No.
No, this is MC. No, that's fine. No, that is not a problem. But why is TD not updating? That is my TD was updating, right? So let's actually. Oh, okay. That's possible that TD is not updating because no episode has finished. Okay, that's actually interesting. See, what will happen is TD it will keep oscillating until, and every time reward is 0. So when the reward is 0, then nothing changes. Gamma is 1. So VS1 and VS, everything, until you reach once, also you need to reach the terminal state at least once. Otherwise, things will not update. Until you reach the terminal state, what happens? All my current estimates are 0.5. So VS1 minus VS is 0. Reward is also 0. So this whole thing is 0. So I will not update. So I need to actually, run maybe 20. Oh, sorry. Let's do the 20 here. Oh, what is happening with my episodes? They're suddenly becoming very long. Or have I made a mistake? Yeah, okay. So this now looks better. Let me actually also print whenever I update. Let me also print the episode. So let's print the episode. Okay, so what TD was doing, so far TD was not doing anything. Okay, now after it reached the episode, so 343, it's pretty much long episode, and the terminal was 6. Now I'm running the MC update completely for the first time. So what MC did was MC, again, this. Okay, fine. Let's live with that. Basically, ignore the first and last because they are always going to be 0. So what MC did was MC updated 1, 1, 1, 1, 1 actually. So MC updated the values for these to be 1 up to this point. Okay, so basically what it thought was it's very beneficial to be at anywhere from 2 to 5. 0, 1, 2 to 5. If I'm at 2 to 5, I've only seen one sample, right? And I have visited all states from 2, 3, 4, 5, and I have finally got my reward. So what it has thought so far is, if I start anywhere from 2 to 5, I'll definitely get the reward. But that is because it has only seen one sample. It will also happen that sometimes it will not get the reward, right? Okay. So next episode is 343210. But before I call the MC, TD keeps updating. Okay, so TD keeps updating this already. So essentially what has happened after the first episode, TD only updated the last value. Okay, because temporal difference only works on the, so the last terminal state had reward 1, the temporal difference only worked on the previous state. So then next state what happened? MC unfortunately ended with a, everybody, and ended with a 0 at the end. So then MC backtracked and figured no. I was so the thing I was thinking is not that good. It actually reduces the estimates for all the states, and particularly for this state the estimate goes a lot down, because it now thinks that if I am ever at state 1, I'll never get the reward, because my only sample for being at state 1 leads me to 0. Okay, so basically this is what keeps happening. Now let's actually and what happened to TD is it actually then the next episode has not finished, but now it already had some update on this particular value, and it actually keeps updating the other values here and there, and so on. Okay, so now we can switch off the print statements, and we can actually, I'll give you the notebook to try these things out on your own, but let's so let's actually try this for a large number. So let's say 100. Oh, sorry. Yeah, so after 100, so actually the true values should be 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6. Okay, so that's what the true probability should be. However, no, sorry, not probabilities. The true expected rewards for each state should be. So after 100, you see that not much has really happened. After maybe 500, this is almost, so 0.16 should have been the case, or 0.17 should have been the case. So TD has kind of in many places almost Yeah, in both actually things have happened a bit, but yeah. So let's do that for 1,000. Okay, so 1,000, you see MC is still not at par. In some cases, TD is probably slightly better, right? So actually, um, um, one can compute the exact exact mean squared error and stuff like that. But now this is the exact Monte Carlo. You could also try the const Monte Carlo with the alpha and so on. So essentially, if you do 5,000, then I think both will kind of converge pretty much. Okay, so this is what is going to happen. Now let's go back to our slides. So numerically, then what we know is TD will convert much faster. And why? Because it doesn't have to wait to get to the end of the episode. Let me start the slideshow. Okay, it doesn't have to wait to get to the end of the episode to be able to update things. So now, so that was just for the evaluation part. Things get interesting only when we can update, we can learn policy or control. Um, so for that, we need to learn the action values. And this method is called SARSA. We'll see in a while why is it called SARSA. And intentionally, I have actually kept spaces between them. So the update formula for learning action values will be just analogous to the one for updating state values. Similar to previously, action values are the queues, right? So the queues are queues STAT, Q STAT, you can update it by Q STAT plus alpha times RT plus 1 plus gamma Q ST plus 1 AT plus 1 minus Q STAT. Now for this, what is necessary? Previously, what was necessary is that you need to take the next action and you need to go to the next state. Now you also need to take another action. Okay, so essentially, if you look at this picture, I want to update QSTAT. Okay, so what all I need? I need AT. I need to take AT, then only I can go to ST plus 1. Okay, and then I need to take this also. But for that, I need to first determine what is my AT plus 1. Right, I'm only learning by sample, right? So I'm actually not looking ahead for all actions. I'm only learning by sample. So what is my Q ST plus 1 AT plus 1? I won't know unless I take the AT plus 1. So what is going to happen is I need to look at all this. Once I have taken this action, then sorry, once I've taken this action, then I update QSTAT. Okay, so maybe I could draw arrows from all of them to here, but that would look too cumbersome. But you see the point. This update rule requires that you have come to ST, taken action AT, got reward T plus 1, gone to state ST plus 1, taken action AT plus 1. At this point, you can update the state, update the action value estimate for QSTAT. Okay, now this is called SARSA because to do this, you need this S, this action A, this reward R, another action, another state S, and another action A. So that is what SARSA is for. Okay, so basically you keep having this sequence, right? SAR, 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 but essentially you need a SARSA to update your action values. Now with this, let's look at today. We'll look at the on policy TD control using SARSA. We'll do the off policy in the next class, which will essentially be Q learning. So the on policy TD control will be, we will update policy, update the same policy that we are actually following or behaving. So initialize QSA arbitrarily for all state action pairs. Now, again, let me remind you here, I just assume that all state action pairs means all state action pairs that are admissible from the states. So some states may not allow you to take certain actions. So those are, implicitly not considered, except Q of the terminal state for any action is equal to 0. Now loop for each episode. Now each episode, we are writing here each episode, but it doesn't mean that you need to actually have different episodes. uh, it's also okay if the episode is very long. However, you need to have at least one episode somehow, right? So basically, otherwise the thing that we saw will not work. So you need to have some terminal states in case the rewards only come at the terminal states. Okay, so otherwise if the rewards are obtained in in all states, different kinds of rewards, like in your life and so on, so it's not that you only get your rewards when you die. So, right, so you get rewards every here and there, so then it's okay, then you don't need to have at episodes ending. So initialize start state as 0, some start state is 0, choose action A0 from A0 based on the policy derived from Q. So this means you currently have some state action values, maybe that is initialized, or maybe in between state, in between step where you have already learned something. So basically you keep doing, but you choose the action A0 based on that. For each state step T in the episode, again you keep taking action and get the reward. um, I'm sorry, it should be RT plus 1, I think. Yeah, I'm sorry. So you get the reward and ST plus 1. uh, then choose action, the next action also from the next state, and then you update it. Okay, let me actually correct it. It should be, I'm pretty sure it should be ST plus 1. Just a moment. Yeah, so this is RT plus 1, and this is also plus 1. Yeah, okay, so you update in this way. Now again, this should have been a small q. Okay, so until you reach the terminal state. So this policy thing, however, you can incorporate other various kinds of relaxations and epsilon greedy approach or whatever you want into this. Um, yeah, I mean, basically you can incorporate other concepts of doing this better, but essentially this is your on policy TD control. All right, any question on this as of now? Okay, good then. So I think then that's yeah. So that's it for today. And yes, there are a few errors in the slides which I will correct and send it to you. Let me stop the recording.